You learn about several algorithms for computing word embeddings. And another algorithm that has some momentum in the NLP community is the GloVe algorithm. This is not used as much as the word-to-vec or the skipgram models, but it has some enthusiasm because I think in part of its simplicity. Let's take a look. The GloVe algorithm was created by Jeffrey Pennington, Richard Socher, and Chris Manning, and GloVe stands for Global Vectors for Word Representation. So previously, we were sampling pairs of words, context and target words, by picking two words that appear in close proximity to each other in our text corpus. So what the GloVe algorithm does is it starts off just by making that explicit. So let's let xij be the number of times that a word I appears in the context of J. And so here I and J play the role of T and C. So you can think of xij as being x subscript tc, but you can go through your training set corpus and just count up how many words does a word I appear in the context of a different word J. How many times does a word T appear in the context of a different word C? And depending on the definition of context and target words, you might have that xij equals xji. And in fact, if you're defining context and target in terms of whether or not they appear within plus minus 10 words of each other, then it would be a symmetric relationship. Although if your choice of context was that the context is always the word immediately before the target word, then xij and xji may not be symmetric like this. But for the purposes of the GloVe algorithm, we can define context and target as whether or not the two words appear in close proximity, say within plus minus 10 words of each other. So xij is a count that captures how often do words I and j appear with each other or close to each other. So what the GloVe model does is it optimizes the following. We're going to minimize the difference between theta I transpose ej minus log of xij squared. I'm going to fill in some of the parts of this equation in a little bit. But again, think of I and j as playing the role of t and c. So this is a bit like what you saw previously with theta t transpose ec. And what you want is for this to tell you how related are those two words. How related are words T and C? How related are words I and J? As measured by how often they occur with each other, which is affected by this xij. And so what we're going to do is solve for parameters theta and e, really using gradient descent, to minimize the sum over I equals 1 to 10,000, sum over j from 1 to 10,000 of this difference. So you just want to learn vectors so that their inner product is a good predictor for how often the two words occur together. Now, just some additional details. If xij is equal to 0, then log of 0 is undefined as negative infinity. And so what we'll do is we won't sum over the terms where xij is equal to 0. And so what we're going to do is add an extra weighting term. So this is going to be a weighting term. And this will be equal to 0 if xij is equal to 0. And we're going to use the convention that 0 log 0 is equal to 0. Right, and so what this means is that if xij is equal to 0, just don't bother to sum over that xij pair, so then this log of 0 term is not relevant. So this means the sum is a sum only over the pairs of words that have co-occurred at least once in that context-target relationship. The other thing that f of xij does is that there's some words that just appear very often in the English language, like this is of a and so on, sometimes these are called stop words, but there's really a continuum between frequent and infrequent words. And then there are also some, infrequent words like during, which you actually still want to take into account, but not as frequently as the more common words. And so the weighting factor can be a function that gives a meaningful amount of computation even to the less frequent words like during, and gives more weight but not an unduly large amount of weight to words like this is of which just appear a lot in language. And so there are various heuristics for choosing this weighting function f that neither gives these words too much weight nor gives the infrequent words too little weight. So you can take a look at the GloVe paper that I referenced in the previous slide if you want the details of how f can be chosen to be a heuristic that accomplish this. And then finally, one funny thing about this algorithm is that the rows of theta and e are now completely symmetric. So theta I and ej are symmetric. In that if you look at the math, they play pretty much the same role, and you could reverse them or swap them around, and they actually end up with the same optimization objective. So one way to train the algorithm is to initialize theta and e both uniformly at random, run gradient descent to minimize this objective, and then when you're done for every word, to then take the average. So for a given word w, you can have e final to be equal to the embedding that was trained through this gradient descent procedure plus theta trained through this gradient descent procedure divided by 2, because theta and e in this particular formulation play symmetric roles, unlike the earlier models we saw in the previous videos where theta and e actually played different roles and couldn't just be averaged like that. So that's it for the GloVe algorithm. I think one confusing part of this algorithm is, if you look at this equation, it seems almost too simple, right? How could it be that just minimizing a squared cost function like this allows you to learn meaningful word embeddings? But it turns out that this works. And the way that the inventors ended up at this algorithm was they were building on a history of much more complicated algorithms like the neural language model, and then later there came the word-to-vec skipgram model, and then this came later and really helped to simplify all of the earlier algorithms. Before concluding our discussion of algorithms for learning word embeddings, there's one more property of them that we should discuss briefly, which is that we started off with this featureization view as the motivation for learning word vectors, where we said, well, maybe the first component of the embedding vector could represent gender, the second component could represent how royal it is, then the age, and then whether it's a food, and so on. But when you learn a word embedding using one of the algorithms that we've seen, such as the GloVe algorithm, which we just saw on the previous slide, what happens is you cannot guarantee that the individual components of the embeddings are interpretable. Why is that? Well, let's say that there is some space where the first axis is gender and the second axis is royal. What you can't do is guarantee that the first axis of the embedding vector is aligned with this with these axes of meaning of gender, royal, age, and food. And in particular, the learning algorithm might choose this to be the axis of the first dimension. So given maybe a context of words, so the first dimension might be this axis, and the second dimension might be this. Or it might not even be orthogonal. Maybe it'll be a second non-orthogonal axis. Could be the second component of the word embeddings you actually learn. And one way to see this is if you have a sophisticated understanding of linear algebra, is that if there was some invertible matrix A, then this could just as easily be replaced with A times theta I transpose A inverse transpose EJ. Because we expand this out, this is equal to theta I transpose A inverse transpose times EJ. And so the middle term cancels out and you're left with theta I transpose EJ, same as before. Don't worry if you didn't follow the linear algebra, but that's a brief proof that shows that with an algorithm like this, you can't guarantee that the axis used to represent the features will be well aligned with what might be easily humanly interpretable axes. And in particular, the first feature might be a combination of gender and royal and age and food and cost and size, and is it a noun or an action verb, and all the other features. So it's very difficult to look at individual components, individual rows of the embedding matrix, and assign a human interpretation to that. But despite this type of linear transformation, the parallelogram math that we worked out when we're describing analogies, that still works. And so despite this potentially arbitrary linear transformation of the features you end up learning, the parallelogram math for figuring out analogies still works. So that's it for learning word embeddings. You've now seen a variety of algorithms for learning these word embeddings, and you get to play with them more in this week's programming exercise as well. Next, I'd like to show you how you can use these algorithms to carry out sentiment classification. Let's go on to the next video.